Right now, your incredibly expensive, razor-thin laptop is basically actively fighting the laws of physics.
Oh, absolutely. It's a miracle it works at all.
Right. I mean, if it were actually made entirely out of that beautiful, seamless, brushed aluminum they show you in the commercials, it would be completely useless. It would just be a very expensive brick.
The literal Faraday cage.
Exactly. It would trap all the radio signals inside, block everything from the outside. You'd have zero Wi-Fi, zero cellular data, no Bluetooth.
Yeah, to get that device to actually communicate with the world, engineers have to deliberately compromise that perfect metal shell.
And that brings us to our mission for today. So welcome to the deep dive. We are taking a really heavily detailed look at the invisible ecosystem of technology that, we carry in our pockets and our bags every single day.
The stuff we completely take for granted.
100%. Our stack of sources today draws directly from official IT training materials. Specifically, we're looking at the CompTIA A+ certification, Module 9. This focuses on supporting mobile devices, and we're zeroing in on objectives 1.2 and 1.3.
What's fascinating here is that while those specific objectives cover the hardware accessories, the connection types, network protocols, the underlying architecture isn't just for IT professionals trying to pass a test.
No, not at all.
It is basically the fundamental blueprint for how modern society communicates. It's the relentless, almost obsessive drive to balance two totally opposing forces.
Portability versus power, right?
Exactly. On one side, you have the demand for extreme portability. You want that solid, indestructible metal slab aesthetic. But on the other side, you have this absolute necessity for massive desktop-level connectivity.
Yeah, and every millimeter of a mobile device is a battleground for that. Every single port, every microscopic antenna band they cut into the chassis, it's a huge compromise in this massive tug-of-war.
It really is.
So the goal for you, listening right now, is to basically shatter that illusion of magic. We want to transform how you view these devices. Take you from just a casual user who taps on glass all day to someone who truly grasps the deep engineering logic.
The how and the why behind the hardware.
Right, because before these machines can talk to cell towers or Wi-Fi routers, we have to actually physically talk to the machines. We have to bridge that gap between human biology and digital logic.
The human-machine interface. It's where analog intent becomes binary data.
Okay, so let's unpack this, starting with the physical inputs. I'm looking at the CompTIA outline, and there is one input device here that feels like a complete historical anomaly, but it just refuses to die.
I think I know exactly what you're going to say.
I'm talking about the TrackPoint. For anyone who hasn't used one, it's that tiny, usually red, rubbery nub embedded directly in the middle of a laptop keyboard, usually wedged right between the G, H, and B keys.
The classic ThinkPad nub.
Yes. You see it on Lenovo ThinkPads, some Dell and HP business laptops. And my assumption has always been that this is just, legacy hardware for people who refuse to learn how to use a multi-touch glass trackpad.
Just stubborn old typists, right?
Right. I mean, why do we still dedicate prime motherboard real estate to a tiny rubber eraser from 1995?
Well, calling it an eraser severely undersells the biomechanical engineering at play there. The survival of the pointing stick isn't about stubbornness at all. It's actually a masterclass in eliminating context switching for power users.
Context switching, like breaking your focus.
Physically breaking your focus, yeah. When you are touch typing at, say, 90 words a minute, your hands are anchored to the home row. To use that massive glass trackpad you mentioned, you have to break your physical flow state.
You have to move your hand down.
Exactly. You physically lift your wrist, move your hand down, manipulate the cursor, and then you have to recalibrate your hand's position back over the keys to start typing again.
I mean, sure, but that takes maybe half a second.
Right. But multiply that half second by 1,000 interactions a day.
Oh, yeah, that adds up.
It's an ergonomic nightmare for sustained coding or heavy data entry. The TrackPoint operates on a completely different mechanical principle. It's actually an isometric joystick.
Isometric? Wait, meaning it doesn't move?
It doesn't actually move. It feels like it moves because the rubber squishes, but beneath that little red cap are these microscopic strain gauges.
Strain gauges, like it's measuring pressure.
Yes. When your index finger applies lateral pressure, the gauges measure the mechanical deformation. They translate that microscopic flexing into cursor velocity.
So it's reading the tension of my finger, not physical travel distance.
Exactly. And because it sits dead center right between your index fingers, you can navigate a huge spreadsheet or a complex software interface without your palms ever leaving the palm rest.
That actually makes total sense. That explains why it feels so hypersensitive when you first use one. It's a precision instrument for people prioritizing pure input speed over, like, sweeping trackpad gestures.
Right. It's purely functional.
But the source material also pivots from that really hyperspecific keyboard-bound tool to how we digitize much broader, free-flowing human movements. Like, touchpads map crude finger swiping, but the documentation spends significant time on graphics tablets and styluses.
Well, the stylus represents a much, much deeper problem that engineers had to solve.
Yeah.
Because, a mouse or a TrackPoint, it translates abstract directional intent into a cursor, up, down, left, right.
Sure.
But a stylus has to digitize thousands of years of human muscle memory. It has to perfectly replicate handwriting and drawing.
And a modern stylus is doing a lot more than just telling the screen where its tip is resting, right?
Right.
The CompTIA A module specifically highlights precision input and handwriting recognition.
Right. It's not just a plastic stick anymore.
Yeah. If a stylus is just a piece of plastic tapping a touch-sensitive glass layer, how is the device extracting enough data to recognize complex handwriting or, like, brushstrokes?
Well, the assumption there is that the stylus is passive, like your finger. But in reality, a modern stylus is heavily active. It relies on complex physics, things like electromagnetic resonance or EMR, and active electrostatic technology.
Electromagnetic resonance. Okay, break that down for me.
So the screen of a tablet isn't just displaying pixels. It actually has an active digitizer layer built right behind the LCD. And that digitizer is constantly projecting an electromagnetic field outward.
Like just radiating a field straight out of the glass.
Exactly. When you bring an EMR stylus near the screen, there's a little copper coil inside the pen that harvests energy from that magnetic field. It's very similar to wireless charging.
Oh, wow. So the screen is wirelessly powering the pen while simultaneously tracking where it is.
Yes. It uses that harvested power to wake up a tiny internal microchip inside the pen. And once the pen wakes up, it starts transmitting its own data back to the digitizer.
Wait, what data is it sending back? I thought the screen was tracking the pen.
The screen tracks the location. But the pen isn't just reporting X and Y coordinates. The pen has its own internal sensors, measuring the exact physical pressure being applied to the tip.
Oh, so the pen knows how hard I'm pressing.
Yes. It can often distinguish between over 4,000 different levels of force. It also measures the physical tilt of the barrel based on how the electromagnetic signal deforms.
That is wild.
It packages all that telemetry and fires it back to the screen hundreds of times a second.
Which means, okay, so when I'm drawing in Photoshop, the thickness of a digital ink line isn't just software guessing what I want based on the size of my finger.
No, it's a real-time mathematical rendering of the microscopic physical compression of that pen tip.
We are literally converting the analog weight of a human hand into a digital data stream. That is a massive leap from a pointing stick.
It's an incredible piece of engineering.
And if the stylus digitizes the hand, the audio and visual peripherals digitize the face and the voice. The sources break down microphones, webcams, speakers, and external displays.
Right. And if we connect this to the bigger picture, the role of these AV components has undergone just a radical shift over the last few years.
Oh, for sure.
I mean, 10 years ago, a laptop webcam was just a 720p afterthought. You used it for grainy holiday Skype calls with your grandparents. The microphone was a cheap condenser they just drilled next to the keyboard. They were essentially multimedia toys.
But the shift to remote and distributed work flipped that completely, didn't it?
Entirely. Your physical presence in a corporate office has been replaced by your digital fidelity on a network.
Right. The mobile device itself, the central processing unit, the RAM, the solid-state drive that is basically just a brain in a jar.
Exactly. The AV peripherals are the senses.
Yeah, because if you bring a phenomenally powerful laptop to a vital corporate negotiation, but it has a poorly isolated microphone that picks up the laptop's internal fan noise.
Which happens all the time.
All the time. And a camera sensor that can't handle the dynamic range of the backlit window behind you, your professional presence is instantly degraded. You look unprofessional.
You do, but the engineering challenge there is brutal because you have consumers demanding bezels around their screens that are practically non-existent. We're talking maybe 2 millimeters thick.
Yeah, we want the screen to go edge to edge.
But they also expect broadcast quality video out of the camera jammed into that tiny little gap.
How is that even possible?
Well, the physics of light simply do not favor miniaturization. A good camera needs a physically large image sensor to capture photons. Squeezing a CMOS sensor into a 2 mm bezel means the individual pixels on that sensor have to shrink to a fraction of a micron.
And smaller pixels mean less light.
Exactly. They capture less light, which introduces all that digital noise and grain. So to compensate, manufacturers are forced to lean on the processor. They use highly aggressive machine learning algorithms in real time to denoise the image, balance the exposure, and basically artificially map your face.
Wait, artificially map it? So I'm not even sending real video anymore?
Not really, no. You are transmitting a heavily computed, AI reconstructed approximation of your face.
That is slightly terrifying, but it perfectly illustrates the central theme of this whole deep dive, right? That tension between sleek, ultra-thin design and raw capability,
The eternal struggle.
which naturally forces us to look at how these mobile devices physically bridge to the outside world. Let's talk about port soup.
Ah, the physical I/O layout. The history of consumer technology is literally written in the graveyards of abandoned connectors.
And here's where it gets really interesting for me, because when you look at the physical evolution detailed in the CompTIA images, the older laptops resemble like industrial control panels.
They were massive.
Huge. You have these massive, bulky serial and parallel legacy ports. You've got dedicated video like VGA or those early display ports. You have a whole rim of rectangular USB Type A ports, dedicated audio jacks, the RJ45 Ethernet jack for hardwired networking, full-size memory card readers.
Just a wall of ports.
Right. And then you compare that to modern smartphones or even ultra-thin laptops today, and that entire alphabet soup just collapses. The sources point out that on mobile, we've moved through micro B USB, the older mini B, and now we are essentially standing in the era of the universal USB-C.
Yeah, and the disappearance of those legacy ports isn't just an aesthetic trend so they can make laptops thinner. It's actually a fundamental shift in data transmission architecture.
How so?
Well, think about why parallel ports existed on older machines in the first place. A parallel port sent data simultaneously across multiple separate copper wires. Imagine 8 lanes of highway traffic moving side by side at the same time.
Which sounds faster, right? I mean, more lanes equal more traffic.
In theory, yes.
Yeah.
But in physics, no. As processor speeds increased, pushing electrical signals through those parallel copper wires at higher and higher frequencies created a massive problem. It's called crosstalk.
Crosstalk, like the wires are interfering with each other.
Exactly. The electromagnetic field of one wire would bleed over and interfere with the wire right next to it. The data would start arriving out of sync. It was like those 8 cars drag racing down a highway and just violently crashing into each other.
Oh, wow. So you can't just keep adding lanes.
No. The engineering solution was to abandon the parallel lanes entirely and move to serial transmission, sending data single file down an incredibly fast, highly shielded single lane. That is actually what Universal Serial Bus USB means.
Oh, universal serial bus. So we didn't just change the shape of the plug to make it look nicer. We fundamentally changed the physics of how the electrical pulses are organized so they don't destroy each other at high speeds.
Precisely. And that entire evolution culminates in USB-C.
But wait, USB-C isn't just one serial lane, is it? Because the training materials specify that a modern USB-C connection is replacing the power cable, the video cable, and the data cable all at once.
Right.
If I have a single oval-shaped port the size of a breath mint on the side of my laptop, how is it juggling power, a 4K monitor, and an external hard drive, all without crashing?
The genius of USB-C lies in its pin architecture and multiplexing. Inside that tiny reversible connector are 24 microscopic pins, and they're totally dynamic.
Dynamic how?
When you plug a USB-C cable into a modern laptop, a dedicated microcontroller instantly negotiates with whatever device is on the other end. This is incredibly rapid digital handshake.
Yeah.
The port can dynamically reassign those 24 pins on the fly.
Oh, so it dictates the traffic patterns based on what I just plugged in.
Exactly. If you plug in a high wattage power adapter, the pins negotiate the power delivery protocol, allowing up to 240 watts of electricity to flow in and charge the battery.
Right.
But if you unplug that and plug in a monitor, the port activates what's called alternate mode. It instantly reassigns high-speed data pins to carry native DisplayPort video signals instead.
It is an aggressively intelligent physical bridge. We didn't actually lose the functionality of the old port soup. We just built a smart toll booth that routes all the traffic through a single reversible tunnel.
That's a perfect way to put it.
Which sets up the next critical piece of the CompTIA hardware breakdown. Because a single universal tunnel is great for a phone on the go, but when a power user sits down at a desk, they still need to break that single connection back out into a dozen different peripherals.
Right. You still need your monitor, mouse, keyboard, network.
Exactly. And the materials highlight two very distinct pieces of hardware for this, and honestly, consumers get them confused constantly: the port replicator and the docking station.
Oh, this is a huge point of confusion.
Yeah.
The distinction here is vital for anyone managing a fleet of hardware or building a workstation, and it really comes down to how deeply the external device penetrates the laptop's internal architecture.
Because from a layman's perspective, they look identical. You take your laptop, you plug it into a plastic brick on your desk, and that brick has an Ethernet jack, HDMI ports, and extra USB slots.
They do look the same.
The outline defines a port replicator as something that simply expands connectivity. It provides a full complement of standard and legacy ports. But a docking station, it says, functions as a replicator, but allows the laptop to operate like a full desktop. It drives external monitors, provides proprietary power, links peripherals.
Right.
I have to push back on this a bit. If both devices just give me extra ports to plug a monitor and a mouse into, aren't we just splitting hairs over marketing terminology?
It's totally understandable why you'd think that. But this raises a really important question about how data is processed versus how it is simply routed.
Okay, walk me through it.
Let's look at the port replicator first. A replicator basically operates on the outside of the computer's logic. It is just a passive hub. If you plug a replicator into a standard USB port on your laptop, you're taking the maximum bandwidth of that single USB lane and just chopping it into smaller pieces.
Oh, I see.
If you plug an external hard drive and a 4K webcam into a replicator, they are fighting each other for bandwidth on that single USB lane going back into the computer. The replicator has no processing power of its own.
So the laptop's processor is still doing all the heavy lifting. It's managing the traffic jam right at that single USB port.
Yes. A docking station, historically and architecturally, is vastly more invasive. When you plug into a true docking station, usually via a really high bandwidth Thunderbolt connection or one of those proprietary bottom-mounted connectors on enterprise laptops, you are bypassing standard external USB logic entirely.
Wait, bypassing it? Where does the data go?
You are using PCIe tunneling to connect directly into the laptop's motherboard.
Meaning the dock isn't an external accessory anymore. It literally becomes a physical extension of the laptop's central nervous system.
Exactly. A high-end dock isn't just dividing a signal. It often has its own dedicated network interface controllers, its own audio processing chips, massive power delivery circuits. It takes the thermal and processing load completely off the laptop's internal components.
It electronically transforms this highly portable, thermally constrained chassis into a permanent, heavy-duty powered desktop workstation.
Right.
I see the difference now. The replicator is basically a power strip you plug into an outlet. The dock is like taking an electrical subpanel and wiring it directly into the house's main breaker.
That's exactly it.
And what blew my mind in the module is that this level of architectural extension isn't restricted to laptops anymore. The material specifically covers smartphone and tablet docks.
This is the ultimate realization of that miniaturization trend we were talking about.
How so?
Well, the processor inside a flagship smartphone today utilizes ARM architecture that is so incredibly thermally efficient and so mathematically dense, it actually rivals or beats the standard processors that powered desktop computers just 5 years ago.
So the bottleneck is no longer that the phone isn't smart enough.
No, not at all.
The bottleneck is just that a 6-inch screen and a virtual thumb keyboard are terrible interfaces for writing a massive spreadsheet or editing a video.
Which is exactly why the smartphone dock exists. You drop your phone onto an angled cradle on your desk, and using that alternate mode over USB-C we just discussed, the phone instantly pushes a full windowed desktop operating system to a 27-inch external monitor.
It connects to your mechanical keyboard, your laser mouse.
Yeah. All the computational math, all the memory caching, it's all happening inside that tiny glass slab in the dock.
Yeah.
But your human interface is suddenly completely desktop class.
You could theoretically run an entire enterprise environment without ever purchasing a traditional desktop tower again. The raw horsepower in our pockets is staggering.
It really is.
But of course, all of that local processing power is completely useless if the device is isolated from the global network. We've covered the physical cables and the docks. We need to sever the physical tether and move to the invisible web. Let's talk about cellular data and the microscopic piece of silicon that makes it all legal. The SIM card.
Ah, the SIM card. It is the most universally utilized and least understood cryptographic device on the planet.
Really? The CompTIA A module defines SIM as Subscriber Identity Module. It identifies your device to the carrier network. It stores your phone number, subscriber info, some authentication keys, and it's strictly required for cellular service.
Right.
Visually, the sources trace this incredible shrinking act. We start with the standard SIM, which was basically the size of a credit card cut in half, then down to the micro, and now the nano SIM, which is quite literally just the gold contact pads with zero plastic border.
Just the chip itself.
Yeah. And now we are shifting entirely to eSIM, completely embedding the hardware into the motherboard. But I have to admit, before I read this material, I assumed a SIM card was just a tiny, cheap USB flash drive that held my phone number and some contacts.
Oh, that is a very common misconception. A SIM card does not merely store data. It is actually an independent, highly secure microcomputer.
Wait, it's a computer?
Yes, it has its own central processing unit, its own volatile memory RAM, its own operating system, and a highly fortified storage sector that the host phone cannot even read.
Hold on. My incredibly smartphone can't read all the data on the tiny SIM card plugged into it.
It absolutely cannot.
Yeah.
And that is by design. If we look at the cryptographic architecture, the SIM card is a mathematical lockbox. Inside that locked secure enclave is a deeply guarded cryptographic key called the key, or the authentication key.
Okay, the key.
This key is permanently burned into the silicon by the carrier at the factory. It never leaves the SIM card. Ever. When your phone powers on, the cellular modem reaches out to the nearest cell tower and requests access to the network.
And I'm assuming the tower asks for a password.
Actually, no. The tower does not ask for a password. Instead, it generates a completely random number, a mathematical challenge, and transmits it to your phone.
Okay. And the phone hands that challenge to the SIM card.
Yes. The phone passes the random number into the SIM's internal processor. The SIM takes that random number, mixes it with its secret key, using a complex cryptographic algorithm, often called the A3 algorithm, and generates a highly specific mathematical signature, a response.
Okay, I'm following.
The SIM hands only the response back to the phone, which then transmits it to the tower. The carrier's mainframe runs the exact same math on their end. If the signatures match, you are granted access to the network.
That is incredibly elegant. The secret key is never transmitted over the air, so it can't be intercepted. And it's never even exposed to the phone's operating system, meaning a virus on my phone can't steal my cellular identity.
Exactly. It's unhackable authorization.
And the evolution to eSIM doesn't change that underlying cryptography, does it?
No, not at all.
No.
An eSIM is simply a rewritable secure enclave that is permanently soldered to the motherboard. Instead of the factory burning the key into a removable piece of silicon, you download the cryptographic profile over a secure encrypted tunnel.
Which saves physical space inside the device and eliminates a point of mechanical failure, the SIM tray mechanism.
Right. One less hole cut into that perfect metal chassis.
Now, once that mathematical handshake clears and you are officially allowed onto the macro network, the capabilities of that network determine entirely what your mobile device is actually capable of doing. The source material outlines the generations of cellular speed.
The Gs.
Right. We have 3G, used in the early smartphone era, maxing out around 7.2 megabits per second. Then 4G LTE, pushing up to 300 megabits per second. And now 5G, with theoretical limits hitting 10 gigabits per second. I look at those numbers, and obviously bigger is better, but I feel like we lose context for what that exponential growth actually engineers.
We really do. The context requires looking at information theory, specifically the Shannon-Hartley theorem, which essentially dictates the maximum rate at which information can be transmitted over a communications chain.
Okay, so it's not just a dial you turn up.
No.
Yeah.
Going from 7.2 megabits to 10 gigabits isn't just making things faster. It requires completely reinventing the physics of the radio waves.
Explain that transition for me. How do we jump from 3G limits to a 10 gigabit fire hose?
So in the 3G era, the modulation schemes, basically how we alter radio waves to carry ones and zeros, were relatively simple, and we used lower frequency bands. A 7.2 megabit connection meant your phone was essentially a really fancy digital pager.
Right, I remember waiting minutes for a photo to load.
Exactly. It was fantastic for retrieving discrete, asynchronous packets of data, text emails, basic HTML websites, incredibly compressed photos. To get to 4G at 300 megabits, engineers had to implement quadrature amplitude modulation, or QAM.
Quadrature amplitude modulation. Sounds intense.
It is. We started altering both the amplitude and the phase of the carrier wave simultaneously, packing exponentially more bits into every single hertz of frequency.
Which is what enabled real-time streaming, right?
Yes. 4G essentially eliminated the buffering icon. It allowed an app on your phone to maintain a persistent high bandwidth connection with the server. This boasts the entire gig economy.
Like Uber.
Uber relies on thousands of cars constantly streaming their GPS telemetry in real time. Video calls became ubiquitous. You couldn't do that on 3G.
But 5G at 10 gigabits per second seems almost absurdly excessive for a mobile device. I mean, I can stream a 4K Netflix movie perfectly fine on 4G. Why do we need a network pipe that massive for a 6-inch screen?
Because the goal of 5G isn't to make your Netflix movie look slightly sharper while you're on a bus.
What is it then?
The goal is to completely eliminate the network bottleneck so that the heavy processing doesn't have to happen on the device at all.
Oh.
To achieve 10 gigabits, 5G utilizes millimeter wave frequencies. These are incredibly high-frequency radio waves that carry massive amounts of data but have very, very poor range. They require dense networks of small cell towers everywhere.
Like on every light pole.
Right. But when you achieve that speed with nearly zero latency, your phone doesn't need to be a supercomputer anymore. It just needs to be a very fast display.
Wait, so the cloud is doing all the work?
Exactly. You can render complex augmented reality, autonomous driving telemetry, or heavy enterprise software entirely in a cloud data center miles away and stream the raw, uncompressed output to the device instantaneously.
It effectively removes the physical processing constraints from the mobile hardware itself. But of course, maintaining that connection to a tower miles away takes energy. The CompTIA material notes that users can easily toggle cellular data on or off in the device settings to manage connectivity or battery usage.
Pushing a radio frequency signal through concrete buildings and miles of atmosphere to reach a cell tower is an incredibly power-intensive process for a tiny mobile battery.
Which is the perfect rationale for why we need to manage our local airwaves. If I'm indoors or I want to share my macro network connection with other devices, I don't want to rely solely on everyone talking to the cell tower. Let's dive into tethering, Wi-Fi, and the local radio networks.
This is the layer where the mobile device stops being an endpoint and starts acting as a network router.
The classic use case in the training materials is mobile hotspot or tethering. You are in a remote location with terrible or non-existent Wi-Fi, but you have a strong 4G or 5G cellular signal and you need to get your laptop online. You turn on tethering and your phone shares its cellular data.
A lifesaver.
Absolutely. The outline breaks this down into 3 specific protocols: Wi-Fi hotspot, USB tethering, and Bluetooth tethering. My question is, why do I need 3 different ways to share the exact same internet connection?
Well, because each protocol manages the constraints of power, bandwidth, and routing geometry differently. When you activate a Wi-Fi hotspot, you are instructing the operating system on your phone to fundamentally change its networking role.
What's it doing under the hood?
It spins up a DHCP server to assign IP addresses. It activates network address translation, or NAT, to route data packets from the laptop through the phone and out to the cell tower.
It literally becomes a miniature wireless router.
Yes. The advantage is universal compatibility and the ability to connect multiple devices simultaneously. The severe disadvantage is the physics of RF broadcasting.
Because it's transmitting 2 different signals.
Exactly. Your phone is simultaneously maintaining a high-power cellular connection to a tower miles away, and it's actively broadcasting a 2.4 or 5 gigahertz Wi-Fi signal in a bubble around you. This draws massive amperage from the battery and generates significant thermal output. The device will actually throttle its performance to prevent overheating.
So if I'm sitting at a desk and I only need my one laptop connected, leaving the Wi-Fi hotspot on is horribly inefficient. That's where USB tethering comes in, right?
Yes. USB tethering utilizes protocols like RNDIS to encapsulate the Ethernet traffic over a physical USB cable. By using a copper cable, you completely eliminate the massive power drain of broadcasting a local Wi-Fi bubble.
And it's probably faster, too.
Much faster. The connection is shielded, highly stable, immune to local wireless interference, and fundamentally secure. Furthermore, the laptop's USB bus provides 5 volts of power back to the phone, charging the battery while routing the data. It is the architecturally superior choice for a single device.
So what on earth is the use case for Bluetooth tethering? Bluetooth bandwidth is tiny compared to Wi-Fi.
Bandwidth isn't the only metric of value. Bluetooth is an ultra-low power protocol. Imagine you have a cellular phone in your pocket and a Wi-Fi only tablet in your backpack. You want the tablet to quietly sync emails and calendar updates in the background while you travel.
Okay.
If you leave a Wi-Fi hotspot running in your pocket, your phone battery is dead in 3 hours. If you pair them via Bluetooth tethering, the tablet gets a constant trickle of data, sipping just milliwatts of power, and both devices easily last all day. It's an exercise in prioritizing endurance over speed.
That makes total sense. You select the protocol based on the immediate bottleneck battery, speed, or device count. Now, while we are on the topic of local wireless, let's zoom in on standard Wi-Fi mechanics. We've all toggled Wi-Fi on and off in software. The materials mention older laptops having physical hardware switches to cut power to the Wi-Fi card, but the detail that caught my eye is the note on Wi-Fi antenna placement.
We touch back on the Faraday cage problem here.
Exactly. The outline states that mobile devices use internal antennas connected to the Wi-Fi chip, and their specific placement within the chassis ensures the strongest possible signal. But if I have a laptop made entirely of aluminum, how are those antennas actually seeing the router?
The antennas require a non-metallic window. In premium metal laptops, industrial designers and RF engineers fight a constant, brutal war over millimeter tolerances.
Ah.
The Wi-Fi antennas are almost universally routed up through the display hinges and placed at the absolute highest point of the lid assembly.
What, all the way up there?
2 reasons.
Yeah.
First, elevation. Getting the antennas off the physical desk reduces signal reflection and obstruction from the user's hands typing on the keyboard.
That makes sense.
Second, the display housing usually incorporates a plastic bezel, or the metal lid itself has a small, precisely milled plastic cap at the top edge. Radio frequencies at 2.4 and 5 gigahertz have specific physical wavelengths around 4.9 inches and 2.3 inches, respectively.
Right.
The internal antennas are precisely manufactured strips of conductive material to mathematically resonate with those exact wavelengths. They are pressed flat against that plastic window to allow the electromagnetic waves to actually penetrate the chassis.
And on smartphones, it's those little plastic bands you see interrupting the metal frame around the edge.
Yes. And with modern MIMO technology, multiple input, multiple output devices utilize several antennas simultaneously to catch multipath signals bouncing off walls. If you cover one antenna band with your hand, the baseband processor instantly switches priority to a different antenna on the opposite side of the device to maintain the connection.
The physical placement is a highly mapped mathematical geometry. It's incredible how much invisible math is happening just to keep a YouTube video playing when I turn my phone upside down.
It's doing millions of calculations a second just for that.
So we've covered the macro cell networks and the local Wi-Fi networks. Let's go micro. Let's talk about NFC, or near-field communication. The CompTIA A module specifically ties this to contactless payments like Apple Pay and Google Wallet.
The tap-to-pay revolution.
Right. It operates via short-range wireless, literally just a few centimeters, to provide highly secure transactions. The transmission actually activates the reader chip in the contactless terminal, but I want to logic through this. If NFC is just another radio wave, why invent a completely new, hyper-limited hardware standard? Why don't I just broadcast my Apple Pay token to the cash register using Bluetooth?
If you broadcast financial data over Bluetooth, you are creating a catastrophic security vulnerability based purely on the physics of signal propagation.
Because Bluetooth travels 30 or 40 feet in every direction.
Exactly. Bluetooth is designed to broadcast outward to maximize convenience. If your phone is shouting cryptographic payment tokens to a register using Bluetooth, those radio waves are penetrating the walls of the store. A bad actor with a high-gain antenna sitting in a car in the parking lot could passively intercept that handshake.
So with NFC, the limitation is the security.
Proximities is the security.
Yeah.
NFC does not broadcast in the traditional sense. It utilizes Faraday's law of induction.
Induction, like a stovetop.
Similar principle. The NFC antenna in your phone is essentially a flat, coiled wire. The payment terminal has a similar coil. When you bring them within 2 to 4 centimeters of each other, alternating current in the active coil generates a localized magnetic field.
Okay, I'm with you.
This magnetic field literally induces a tiny electrical current in the opposing coil.
So it's not shouting across a room. It's using magnetism to whisper directly into the terminal's ear.
It's called load modulation. It is physically impossible to intercept an NFC transaction from across the room because the electromagnetic field simply does not exist across the room. Furthermore, this induction process can be used to wake up passive chips.
What do you mean by passive chips?
Like a physical credit card. It has no battery, but when you tap it, the magnetic field from the terminal induces enough electricity in the card's internal antenna to power the microscopic chip inside just long enough to process the math and reply.
That is brilliant. You leverage the physical degradation of a magnetic field to guarantee proof of intent. You literally cannot accidentally buy someone else's groceries from the next aisle over.
Exactly.
Now, we've spent this entire deep dive activating incredibly complex radios. We've got cellular modems, Wi-Fi chips, Bluetooth protocols, and NFC coils all running simultaneously. The final piece of the local airwave segment is the ultimate override, airplane mode.
The great silencer.
According to the material, airplane mode is a setting that instantly disables all wireless radios on the device. Cellular data, Wi-Fi, Bluetooth, GPS, and NFC depending on the manufacturer. The historical origin, obviously, is airline regulation, preventing a plane full of cell phones from trying to blast maximum power signals to terrestrial cell towers while hurtling at 500 miles an hour.
Which used to severely confuse the ground networks.
And rapidly destroy your phone's battery as it desperately cranks up the amplifier trying to reach a tower that is moving away too fast.
Right. It was a mess.
Which makes airplane mode essentially the ultimate battery-saving tool if you are in the wilderness without a signal. But the crucial detail the source highlights is that specific features can be selectively re-enabled while the device remains in airplane mode. I find this interesting from an architecture standpoint. Is airplane mode a physical hardware switch-cutting power? Or is it just a software suggestion?
Architecturally, it's a software macro that interacts with the baseband processor.
Baseband processor.
Yeah, a modern smartphone actually has two main operating systems running simultaneously. You have the application processor, which runs iOS or Android and handles your screen and your apps. And you have the baseband processor, which is an entirely separate, highly proprietary chip running a real-time operating system dedicated exclusively to managing the radio functions.
So the OS I interact with is just talking to a secondary computer hidden inside the phone.
Correct. When you toggle airplane mode, the application processor sends a command to the baseband processor, instructing it to power down the RF amplifiers. Originally, this was an absolute kill command for everything. But as consumer behavior evolved, specifically the demand for in-flight Wi-Fi and the use of Bluetooth headphones on planes, the software had to adapt.
Because it's useless to have in-flight entertainment if you can't connect your wireless headphones.
Exactly. So the architecture was modified. Toggling airplane mode now executes a blanket shutoff, primarily targeting the high-power cellular modem to satisfy aviation regulations. However, the application processor retains the authority to selectively tell the baseband processor to wake up the local micronetworks.
Oh, I see.
You can manually toggle the Wi-Fi or Bluetooth rails back on.
Yeah.
You maintain compliance by keeping the macro network silenced, but you regain granular control over your local wireless ecosystem.
It's like shutting off the main breaker to the house, but having a secondary subpanel to keep the lights on in one specific room. You dictate the exact emissions of the hardware.
That's a great analogy.
Well, this has been an incredibly dense and eye-opening journey. Let's do a quick recap of the architecture we've explored. We started with the physical inputs, diving into the isometric strain gauges of the TrackPoint and the electromagnetic resonance that allows styluses to convert human analog pressure into digital mathematics.
We waded through the legacy of parallel ports and discovered how the 24 dynamic pins inside a USB-C connector act as an intelligent toll booth for multiplex data.
We differentiated the simple USB hub logic of a port replicator from the deep PCIe integration of a true docking station, expanding all the way to desktop-class smartphone docks powered by ARM architecture.
We cracked open the SIM card, revealing it not as a memory stick, but as a microscopic cryptographic lockbox running challenge-response algorithms to secure the global network.
We explored the physics of information theory, leaping from the simple modulation of 3G to the millimeter-wave fire hose of 5G. We managed our local connections, comparing the routing logic of tethering protocols, the Faraday cage math of antenna placement, the magnetic induction of NFC, and finally, the baseband isolation of airplane mode.
It is a staggering amount of layered engineering that operates completely invisibly every single time you send a text message.
It really is. Which leaves me, and hopefully you listening, with a final provocative thought. We just traced the relentless physical shrinking of this technology. We went from massive 25-pin parallel ports down to a single reversible USB-C. We went from standard plastic SIM cards down to completely invisible, downloadable eSIM secure enclaves.
Everything is shrinking or vanishing.
Right. As wireless technology like millimeter wave 5G and localized ultra-wideband get infinitely faster and more reliable, and as magnetic inductive charging gets more efficient, are we rapidly approaching a future where mobile devices are just that? A completely seamless, unbroken slab of glass and metal without a single physical port, jack, or slot left on them.
The absolute final death of the physical port.
Exactly. What happens when the physical bridge between devices disappears entirely and every single interaction, power delivery, high bandwidth data, audio, video, is handled exclusively through invisible electromagnetic fields and radio waves?
This can change everything.
I think back to that illusion from the beginning of the deep dive, the magician's stage. Right now, we can still see a few of the trapdoors and wires if we look closely at the edges of our phones. But the engineering trend is clear soon. They're going to seal the box entirely. It's something to ponder the next time you plug in a cable, because the physical cable might just be an endangered species.
It's definitely on its way out.
Well, thank you so much for joining us on this journey behind the screen. Keep questioning the physics of how things work and keep diving deep into the technology that surrounds you. Until next time.